Welcome to this introduction on X-ray photoelectron spectroscopy, or XPS for short. It is also sometimes referred to as electron spectroscopy for chemical analysis. XPS is a non-destructive surface analysis technique that is widely used in material science and engineering to study the chemical composition and electronic structure of solid surfaces. XPS works by measuring the kinetic energy and intensity of electrons that are emitted from the surface of a sample when it is exposed to a beam of X-rays. By analyzing the energy and intensity of these electrons, XPS can provide information about the chemical composition and electronic structure of the surface. The theory behind XPS is based on the photoelectric effect, which was first discovered by Rudolf Hertz in 1887 and theoretically explained by Albert Einstein in 1905. The photoelectric effect occurs when photons, or particles of light, interact with atoms in a material and cause electrons to be ejected. X-rays are made up of photons with an energy equal to hV, where V is the frequency of the photon and h is the Planck's constant. The kinetic energy, E subscript k, of the ejected electrons is measured by a detector, and this energy is related to the binding energy, E subscript b, of the electrons in the sample by using the photoelectric equation. In this equation, phi is known as the work function, which is the amount of energy necessary to propel the photoelectron from the sample to the detector, and thus this is specific to the spectrometer used. The XPS instrument itself consists of several key components, including an X-ray source, a sample holder, an electron analyzer, an ion gun, and a flood gun. The X-ray source emits X-rays with a specific energy, which is typically in the range of 100 to 2000 electron volts. The X-rays are focused onto the sample where they interact with the electrons in the outermost layer of the material. The electrons that are emitted from the sample surface are then collected and analyzed by the electron detector, which separates the electrons based on their kinetic energy. The kinetic energy of the emitted electrons is related to the binding energy of the corresponding electron energy levels in the sample. XPS can be used to analyze a wide range of materials, including metals, semiconductors, polymers, ceramics, and composites. Some common applications of XPS include quantification of surface chemical composition, characterizing the surface chemistries of materials, such as the oxidation states of metal surfaces or the functionalization of polymer surfaces. It can also identify contaminants on the surface of materials, such as the residual oils or metal ions, and we can also study the electronic structure of materials, such as the density of states. XPS is a surface-sensitive technique, meaning that it is primarily used to study the top few nanometers of a material surface. As such, the ideal samples for XPS are solids with flat, smooth surfaces. Samples that are rough or have irregular surfaces may give misleading or inaccurate results due to variations in the surface chemistry and topology. To carry out XPS measurements, a carefully prepared solid sample is mounted onto a sample holder or a sample stage using an adhesive or double-sided tape. Powdered samples can also be analyzed using XPS, but they require special handling and preparation to ensure accurate results. The powder must be spread out as thinly and evenly as possible on a flat substrate, such as a piece of adhesive tape, ensuring loosely bound powder is removed to avoid particles entering the internals of the XPS machine. The mounting process should be carried out carefully to avoid any contamination of the sample surface. Once the sample is properly mounted to the sample holder, it is placed inside the sample pre-chamber, where the machine slowly brings it to vacuum. The sample is typically loaded into the instrument under vacuum to prevent any exposure to air or moisture that could affect the results. XPS data is typically presented in two forms: survey scans and high-resolution spectra. The scanning survey scans all the binding energies from 0 to 1300 electron volts. High-resolution XPS spectra can also be obtained and gives information on the different contributions of an overall peak in the survey scan. These different contributions are caused by chemical shifts, which is defined as emitted photoelectrons being affected by neighboring chemical environments, such as specific bond types. As such, the high-resolution spectrum gives information on the types of bond that the elements in the sample have. The image here shows a survey-scanned and a high-resolution XPS spectra for polyethylene terephthalate, a material often used in plastic bottles. To analyze and interpret XPS data, an understanding of the position and intensity of the peaks is required. The position of the peaks along the x-axis in an XPS spectra indicates the elemental and chemical composition of the sample and is traditionally reported as the binding energy in electron volts. The y-axis of the spectra records the intensity of the surface material, in other words, how much of a particular element is present, typically displayed as the total number of photoelectron counts per second. Polyethylene terephthalate, with this chemical formula, contains carbon, oxygen, and hydrogen. Since XPS can't identify helium or hydrogen, only the peaks identifying carbon and oxygen are visible on the survey scan, where oxygen 1s is displayed at 520 electron volts and carbon 1s at 300. The label 1s describes the core electron shell the photoelectron was emitted from. A small peak of oxygen 2s is also observed at 20 electron volts. However, the oxygen 1s peak is used for analysis instead because of its much larger intensity. For polyethylene terephthalate, the carbon 1s and oxygen 1s peaks are observed in the higher resolution spectra. The different bonds associated with the chemically shifted peaks are highlighted in color and correspond to the different carbon and oxygen bonds as shown in the chemical formula. The ratio of the different intensities of the peak are a direct indication of the amount of each bond type present. According to this spectra, there exists 6 green carbons that are present in the aromatic ring, whereas there are only 2 yellow ester carbons and 2 singly bonded blue carbon-oxygen bonds. This explains the 3:1 ratio in the intensity of the peaks of the corresponding bonds. Ion sputtering involves bombarding the surface of a sample with high-energy ions, such as argon ions, to remove a thin layer of material. By performing XPS analysis at different depths after each ion sputtering event, researchers can obtain a detailed picture of the surface composition and electronic structure as a function of the depth of the material. This can be particularly useful in studying thin films, interfaces, and other complex surfaces where the properties can vary with depth. Here, an example is shown of depth profiling with XPS. Stainless steel can be used as a fuel cell separator. However, it's not conductive enough and can lead to chromium leaching, which poisons the neighboring catalyst. To solve this issue, a thin coating of gold is applied. XPS analysis, using ion sputtering and depth profiling, was used to analyze the chemical composition of the coating as a function of depth. The graph here shows that when the gold coating on top of the stainless steel substrate is too thin, indicated by the graph on the right-hand side, chromium migration is observed, indicating leaching of chromium from the steel to the gold layer. When a thicker layer of gold is coated, no chromium is observed in the depth profile graph. Here, XPS depth profiling is successfully used to determine the optimum thickness required for the gold layer to prevent poisoning of the catalyst in a fuel cell. Overall, XPS is a powerful technique for studying the surface chemistry and electronic structure of materials. Its non-destructive nature and high sensitivity make it a valuable tool for a wide range of applications in material science and engineering. This concludes the video on XPS. Thank you for watching, good luck in the lab, and if you need any help, make sure to contact your lab supervisor.